Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell down there. You'll get notifications for this series and a bunch of other ones on our channel. We're doing multivariable calculus. We're in chapter 3, which is vector calculus. And now we're going to do 3.3, which is the fundamental theorem of line integrals. This is going to help us give conditions for what we're going to do this lecture. We're going to do the fundamental theorem of line integrals. And then we're going to give conditions for when we have a conservative vector field f over the plane R2. Let's get to it. Recall from functions of one variable, if f prime of x is a continuous function on an interval ab, then the integral of f prime of x by the fundamental theorem of calculus part 2 is f of b minus f of a. What that's saying in words is the right hand side is the total change of a function f. What this says is to get that total change of a function f, you would take the integral of the rate of change, and that's going to give you total change on an interval. Viewing the gradient function as a kind of derivative of a function of 2 or 3 variables, we have an analogous statement which says that, I know, it's the fundamental theorem of line integrals. I know, this is the exciting part. This is why we're in this, the fundamental theorem of line integrals. What it says is, if we have a smooth curve C, and we have a differentiable function of 2 or 3 variables, and moreover, the technical details, the gradient of that function is, which is a vector field now, is continuous, then with the fundamental theorem of line integrals, the line integral over this gradient of f is equal to f of r of b minus f of r of a. So you can calculate at the boundaries, at the endpoints of that curve, you can calculate f at the boundary of those, and that gives you the integral over a gradient vector. What that says is, if you have a vector field and you could somehow tell whether it was conservative or not, right? Is it conservative? So we want conservative. Is conservative good? Yeah, it's pretty good. So we want conservative, apparently. Who likes conservative? We got a yes from this one. So conservative functions are in. We're going to give conditions right away to tell when we have a conservative function. Why? One of the reasons is, if you have a conservative function, that means there is a gradient which is f. And then computing the line integral of f is the same thing as computing a line integral of a gradient, which is now f of b minus f of a. Yay! Okay, you can go. Let's do that. All right, what is this actually saying? We have a vector field over R2, and we have a curve which is the upper semicircle from 1, 0 to 2, 1. What does that say? That's what it's saying. Eventually, when we talk about orientated curves, this is going to matter because we have to do positively orientated. What does that mean? You actually have to go the other way. You have to go counterclockwise. But right now, what they're saying is just this part of the semicircle. We didn't need that, but it helps to picture what the curve looks like, and this is the problem parameterizing these things. So we don't need this, but what are we going to do with that? Now what we're going to say is what we actually need is, I want to find, first of all, a gradient so that I can view f as a gradient, which is our definition of conservative. I'm not going to worry right now what those conditions are. That's going to be the next 2 theorems, and we're going to be careful with this. Right now I'm just going to find one and show why that's useful to me using the fundamental theorem of line integrals. Therefore, to do this, what does it mean? This is where you can't start proving. What that means is we go back to linear algebra, actually, because these are both vector functions, and we're saying one function of 3 coordinates is equal to another function of 3 coordinates. And when is that true? Well, if you go to linear algebra, I say 2 vectors are equal if and only if all their coordinates are equal. So then, to phrase this, you have to remind yourself who these are. The gradient of little f is going to be the partial of f with respect to x and the partial of f with respect to y. And big F is always P and Q. And now you can ground yourself. That's the first thing you need to find every time you do one of these questions. To find this and use the fundamental theorem of line integrals, which is what I want to do. I want to view my function as a gradient. And then I want to compare this. To find that, what that's going to say is, now do you see the partial of f with respect to x is going to equal p, and the partial of f with respect to y is going to equal q. Therefore, classically, what we start with always, and then this will be an even longer game and more complicated when we have a gradient over R3 instead of R2. You'll have another coordinate. The partial of f with respect to z will be equal to r. And then it's a much more complicated condition, and then showing conservative is much more complicated. We use curl, and then we'll get a condition. For now, we'll start with this guy, x. If I integrate this with respect to x, I'm going to get f back on the left-hand side. And then I'll get the integral of this guy, who's p specifically for us, this guy. Therefore, if I integrate with respect to x, that gives me f of xy is going to equal the integral of y dx, which is equal to xy plus a function of y. Normally we would get a constant of integration, and the argument is if we had a constant and we take the derivative of a constant is 0. And when we take the partial derivative of a function with respect to x, any term that has just y in it will turn to 0 in that partial derivative, and it wouldn't appear. So I have to assume that I have a function entirely of y, and then we have to figure out what that function is. Therefore, now I have a rough idea of who f of xy is, this guy. Then I'm going to use this information to find out who h of y is, and then I have my general function whose gradient is f. And then you're like, what? Then I'm going to actually use that to compute the line integral, which means I can use the fundamental theorem of line integrals. Let's do that. Moving that up, we assume this every time. This is what you have to set up first. If the gradient of little f is big F, we set the partial of f with respect to x equal to p, and the partial of f with respect to y equal to q. And then our first move is we integrate this one with respect to x, and we get this function, and a term that may be entirely a function of y. And then what I do cleverly is I'm going to try to use this equation for some information in the system. Therefore, I'm going to take the partial derivative of f, this one, with respect to y, and then I can set it equal to this one, which I already know it should be. And then I use transitivity of equals, and then I set those two things equal to each other, and I find out what h of y is. How do I do that? This is equal to, the partial derivative with respect to y is now x plus h prime of y. The partial derivative of y with respect to a function of y is the ordinary derivative, and therefore we just get h prime of y. What does that say? From this now, this is the partial derivative. So that should be x plus 2y. Aha! And then I set these, I compare them, and that says I get a condition that says h prime of y must equal 2y. Therefore, I integrate with respect to y, and I'm going to get h of y is equal to y squared plus now k, I guess, because c is my curve, which I disagree with. Gamma is the curve, c is my constant of integration, but some book uses k. This is h of y, and then what's my third step? I now know what my function entirely is. F of xy, therefore, is equal to xy plus y squared plus k. The best part about these ones is, on an exam, you have an immediate check. The partial derivative of f with respect to x is y, which was p of xy, and the partial derivative of f with respect to y is going to be x plus 2y, which was q of xy. So you have an immediate check. That means that the gradient of f is equal to big F. You're like, everyone's like, yay, we're done. It's like, no, now we're going to use that information to now we're going to use this information to actually compute the line integral using the fundamental theorem of line integrals. The best part. All right, they're all down here now. So this one's Petra. Hi, Petra. She wants, everyone apparently really likes, I know, fundamental theorem of line integrals. We're going to do the good part. Exactly. Who wants to see? I do. We can take k equal to 0 because we get a family of functions. So for convenience, I'm just going to let k equal 0. Therefore, our function f of xy is xy plus y squared. Why can I take k equals 0? Because just like the fundamental theorem of calculus part 2, when you do f of b minus f of a and you have the k there, it's going to be k minus k, so it'll cancel anyways. So anyways, we're just going to take the k equal to 0 for simplicity. If it bothers you, leave it in there. You'll see it will disappear in the calculation. By the fundamental theorem of line integrals now, we have that the integral over c, which was, remember, going this way. So we started at this point, 0, 1, and we ended at this point, 2, 1. So our curve is going from 0, 1 down to 2, 1. So this is going to be our b, and this is going to be our a. What that's going to give me is, cat fight, That's what it's going to give me. Curve integral f dot dr. We now have viewed as f as the gradient of little f is big F. What that tells me is I can view this now as the gradient of f dot dr. And then the fundamental theorem of calculus, or of line integrals, now gives me that is f of r of b minus f of r of a, which is going to be f of 2, 1 minus f of 0, 1, which is now equal to, when x is 2 times 1 plus 1 squared minus f of x is 0. So we're going to get 0 times 1 plus 1 squared, which is going to be 3 minus 1, which is 2. That's a whole lot. It's a tour. That's a whole lot better than having to do the line integral over this thing. And then you're going to see in a little bit, when we have multiple curves that we have to do, we're going to have C1 and then C2 and then C3 and then C4. And I really don't want to do line integrals using the definition because I have to parameterize each one of these things and then do it. But if you're a gradient, by the fundamental theorem of line integrals, you do f of b minus f of a, and I get the number 2 immediately instead of having to do all this calculation. So that's why we want the fundamental theorem of line integrals. Let's now give the conditions for when we can actually tell if a vector field is conservative or not. Theorem 1 says that a necessary condition, not sufficient. If you're conservative, then necessarily we have to have that these partial derivatives are equal. So the direct statement, in logic, there's always going to be 4 statements given a declarative statement. The direct statement, which is the mathematical statement we're making, which I'm going to prove in a second. If you are a vector field which is conservative, then the partial of p with respect to y must necessarily equal the partial of q with respect to x. This is not sufficient because we're going to have to change the conditions on d, and then we'll get, if your partials are equal, then you're conservative, and we can have an if and only if statement. What we're going to use with this statement is the contrapositive, actually. Then we'll prove the converse of this statement in the next one when we give an extra condition on our domain. So the contrapositive of this direct statement is the negation of b implies the negation of a in general. In our mathematical statement, that says if these are not equal, then the vector field is not conservative. I never use this statement. The assumption, the antecedent in this declarative statement is that you're conservative. So you're never going to use the statement to try to find conservative functions. You're only ever going to use it via the contrapositive to find not conservative vector fields. Now let's be careful and show then. Let's prove this first. Proof. And then now we're going to prove it. Conditions. Can you prove with the cat? Oh, okay. That was Noodles. He's much more rambunctious. Get back here. Alright, so now what we're going to do is prove this. I claim that I didn't even have to erase that much, and he interrupted my erasing anyways, but that should be good enough because we're going to use Clairaut's theorem, which is really nice that I actually point this out. Clairaut's theorem, everyone seems to really like this, but then it takes a long time in calculus sometimes to get to the punchline of where that would be useful. I know. There it is. We're going to prove it. And here's a direct corollary or consequence of Clairaut's theorem. I'm assuming f is conservative, a priori knowledge. Therefore, oh, I should have done it more technical. For some function f of x, y, there exists a function f of x, y such that big F is this, because I'm assuming he's conservative. What does that say specifically? That says the partial of f with respect to x is equal to p, and the partial of f with respect to y is q. Now take the derivative of those. By Clairaut's theorem, these are going to equal to each other. So the partial of p with respect to y is equal to the partial of f with respect to x with respect to y, which is equal to the partial squared of f, the partial y, the partial x, which by Clairaut is equal to the partial squared f, the partial x, the partial y, which is the partial with respect to x of the partial of f with respect to y, which is the partial of q with respect to x QED. Thank you, Claro. Let's do the next statement. The converse of theorem 1, we have to be much more careful. This is going to be the good one and what you want. But remember, the first theorem says if you don't check your domainy business about simple, that he's got no holes. So good domain, bad. So this is not simply connected. This is simply connected. Simply connected simply means no holes in it. And then we throw you one which has a conservative expression, and then you didn't check that it had a hole, and you're like, it didn't work out. Yeah, you didn't check both of the antecedent conditions of this statement. So technically, this is one of the things you need to check first. Theorem 2 says if you have a simply connected region and a vector field over that, then if the partial of p with respect to y is equal to the partial of q with respect to x, then we have that f is a conservative vector field. And remember what that means. This is existence. There exists a little f of xy such that its gradient is f. And we just showed in the previous example how to actually find that one for a vector field over R2. Let's do an example of using this condition, and be careful. I'll give myself a polynomial, so he's defined over R. R2 has no holes. We'll be good. Example 2, determine if these vector fields are conservative or not. Both of them are polynomials, so in my head I'm going to check these conditions again for you because this is the one that everyone doesn't want to, and then this is how you get it wrong if they're trying to be tricky to you. I'll try not to be too tricky. I'm going to show all the tricks and then you don't get tricked by everyone else. Either way, we're going to be doing this, I'm going to guess. How do I use them carefully to get the right conclusion? If they're not equal, bang, not conservative. If they are equal, make sure your domain is simply connected, then it's conservative. The partial, this is p and this is q for both of them. So in your mind, if you can't see that, that's the first thing you do. You say p this time is 6x plus 5y, and q this time is 5x plus 4y. Or, I don't even really care, watch. The partial with respect to y is going to be 5. And that's also going to be the partial of q with respect to x. And then therefore, no. And 6x plus 5y, I changed them, but it doesn't matter. And 5x plus 4y, or any of those numbers, are polynomials. So the domain of f is R2, which is simply connected. Therefore, f is conservative. And then I can play the game that we played earlier where I can actually find the conservative function because I know it exists. See, now we're not wasting time. We now know this vector field is a conservative function, and you can find it by doing that game, and you're not wasting your time. Otherwise, you may be looking for a unicorn. Oh, unicorns don't exist. I'm sorry. Don't look for unicorns. This could take an awfully long time. Infinity is an extremely long time, especially towards the end. Sorry, Woody Allen, I stole your joke. Let's do the next one. What does this say? After checking both conditions, this is the one you're just like, and then conservative. Careful. What region did they give you, or what's the domain? If your domain is something weird and it has punctures, then this is no good. But this one happens to be polynomial, so our domain was all of R2, which doesn't have any holes, so it's simply connected, and therefore we're conservative. The second one, II, commonly referred to as 2 in English. We have the partial of p with respect to y, in our case, is going to be 0, and then we're going to just get 4x. And the partial of q with respect to x is this. You can put that in there if you want. I'm just being lazy. But that's the partial with respect to x of 4xy minus y cubed, which is equal to 4y. Therefore, the partial of p with respect to y does not equal the partial of q with respect to x. And so we can immediately use theorem 1. that tells me that I actually thought it through and just didn't be like, I want it to be true, so it is. I use Theorem 1 to say, therefore, f is not conservative. So if I make a typo on an exam and I say, find the function f such that the gradient of f is this guy, you're looking for a unicorn. It'll never happen. He's not conservative. No such gradient exists. Please subscribe right here. Hit the notification bell. I'll see you next time, wizards.